Hi, welcome back to my tomography class. Last time we talked about the Schwartz space. The Schwartz space is a space of rapidly decreasing functions. So this includes something like the Gaussian or any polynomial times the Gaussian. They're all going to be inside the Schwartz space. Basically, you want to think that they're going to decay really quickly towards infinity. And this allows you to do, say, take integrals over all of Rn of them. You're always assured that that the integrals are going to be finite, even though the integral bound is infinite. And yeah, and then you can use, say, if you have a double integral on these functions, you can always exchange the integrals because you are guaranteed that the function is going to be in L1. And so this allows you to use the Fubini theorem without really even thinking about it. So you can always exchange integrals, and you don't have to worry about any sort of convergence issues. So that's really nice. And another thing that's nice about it is that it's a topological vector space. Topological vector spaces allow you to talk about continuity and convergence. And so for the Schwartz space, we showed that if you have a sequence of functions inside the Schwartz space that gives you a Cauchy sequence, that Cauchy sequence must converge. That means that if you're ever going to have a convergent sequence of functions for a Schwartz space, it's never going to be not in a Schwartz space. Well, really, that's what convergence means. But basically, as long as your functions are getting really, really close in some sort of metric sense, then they're going to be back in a Schwartz space. So we showed that the Schwartz space is more than just a topological vector space. It is actually a metric space. So all the really basic ideas of metric spaces coming from, say, undergraduate analysis still apply here. So we don't have to bother with what analysts usually like to talk about, which are nets and other things like that. Okay, so with these concepts, what do we do next? So what we're really going to be talking about today are what are called tempered distributions. Tempered distributions sounds really fancy, but really what this is it's the topological dual of the Schwartz space, and that might sound fancy too. So basically, it is a collection of continuous linear functionals over them. Sorry, I deal with the Fox space a lot. Over the Schwartz space. So what are these? A functional is any map that takes you from a vector space to the space of scalars that it is over. So say if you just had the vector space, really basic space of R2, and you take all the vectors x, y, and you map them to the coordinate x, that coordinate mapping is a functional, because x is just a real number. If you take this up to the level of functions, and this is something we're going to be talking about today even, but if you have a vector space of functions, then if you, say, take the evaluation at a particular fixed point, say 0, if you take the evaluation of functional at 0, I'm getting ahead of myself. If you take evaluation of a function at 0, that'll give you a real number, or a complex number depending on the space. And that itself is a functional. Now, all these functions I mentioned before are all linear. So if you take, say, two functions f and g and two scalars alpha and beta, and you say alpha f plus beta g, then evaluation of that linear combination can be broken down into a linear combination of the evaluations. So that's linear. There are examples of nonlinear functionals. Usually we don't talk about that in this context. So for instance, if I take the evaluation of a function at a point and then square it, that's not going to be linear. The dual space for a topological vector space is a space of continuous linear functionals. Now, continuity comes from the fact that we can talk about convergence in the Schwartz space. So basically, if we're applying a functional on a sequence of Schwartz space functions, we can ask, does this converge? If we have a convergent sequence of Schwartz space functions, so does the image underneath the functional converge? And that turns out to be really easy to describe those functionals, or at least continuity is an easy description. So that's nice. And so we're going to go through a whole collection of different basic theorems defining some really principal functionals over the Schwartz space, and we call these tempered distributions. So for instance, there are some regular ones that they're called regular distributions. When you can take a function over Rn, and then you can define a functional that is multiplication by your Schwartz space function by your new function f, that is, say, integrable, and then you integrate that. All that together ends up giving you a functional, and that's called a regular distribution. It turns out that we like these so much that we will even go as far as writing things that aren't actually regular distributions, but we'll write it like they are. And we'll get into that when we get there. The ones that aren't regular distributions are called singular distributions, and these include things like the evaluation of a function at the origin. So yeah. What else are we going to talk about? So what is the point of all this dual space theory? What we're trying to do ultimately is we want to take the Fourier transform of, say, periodic functions, and once we do that, we can talk about sampling theorems, Shannon sampling theory. We can talk about the Nyquist frequency, and a lot of other things that have to do with Fourier transforms. We could start with the Fourier transform on just the space of periodic functions, and then we don't really talk about Fourier transform as much as Fourier series, but we need the Fourier transform for working with the radon transform. In fact, that's how we're going to ultimately invert it. And so if we're going to define Fourier series, we should do this properly, and so we're going to go through the route of tempered distributions. What do I mean by properly? Well, if we take a continuous, a periodic function, we know that the Fourier transform of that is going to be undefined, or at least I'll show you that it is. It doesn't give a well-defined function. The reason why is that it isn't absolutely integrable. And we want to define a Fourier transform on these things. And so the route to doing that via the Schwartz space is to talk about these periodic functions as regular distributions on the Schwartz space. And there is a theory that gives you, that is called, say, the theory of generalized functions, which allows you to apply the Fourier transform to the dual space of the Schwartz space. And so then there, even though the integral would technically diverge, we look at this as sort of a convergent underneath this dual formulation, and we'll get to that later. So that's ultimately the route we're trying to take. So we're going through doing this whole dual space idea so that we can talk about the Fourier transform of periodic functions, and then we'll have a nice closed theory around all of this stuff that we're talking about with the radon transform and inversion and all that stuff. And I'm not alone in taking this approach. If you take a look at a lot of the books that we've been referencing, so for instance, if you take a look at this book on computed tomography, I mean, there is, let's see, the fundamentals of signal processing takes up 50 pages out of this textbook, from page 100 up to 148, and this is the first thing that they talk about in this textbook. I mean, they talk about milestones of computed tomography, just to give you an idea of what's going on and all this stuff, and sort of an introduction, fundamentals of X-ray physics and stuff, which I'm not really an expert on, but before they get to the brass tacks of actually working with the radon transform and doing inversion and all this other stuff, they have to pay the price of going through the fundamentals of signal processing, and that's ultimately what we're building up to. So we'll talk about, when we get there, we'll talk about filters and all these other good ideas. Some other transforms in here. So there's a Hankel transform and whatnot. But one thing at a time. And so right now we're working on building up a theory for Fourier transforms, and yeah. So why don't we stop jabbering, and we can go ahead and jump into it. All right, thanks for listening.
Okay,
So let's go ahead and get started. I apologize if you hear the cat howling in the background and that causes you any anxiety. My wife took the kids out so that I can have some time to record, and yeah, my cat now just decides to go and start crying. He's tortured every day by my children. This is like the only time he has to be free and like relax. And yeah, no, I guess he likes being tortured. Anyways, so yeah, let's go ahead and get started. You don't need to hear about my cat. Alright, so what we're going to be talking about today is tempered distributions. So basically, tempered distributions are members of the dual of the Schwartz space. We call them tempered because when we talk about actual, or not actual, but when we talk about distributions, we're usually talking about the dual space of the space of C infinity functions that have compact support. And so there are fewer of those functions, so it's easier to be in the dual space for that space. And so when you expand your space from being just C infinity with compact support to the Schwartz space, which and so that is a proper inclusion inside the Schwartz space of C infinity functions with compact support. That means that it's harder to be continuous because there's more conditions to satisfy. So tempered distributions, there are less of them, and in a sense that makes them easier to work with. So that's why we talk about these. All right, so we're going to say let S be the Schwartz space with sort of its metric D, which goes from the Schwartz space across the Schwartz space to R plus, defined by the pseudo or seminorms. So we have P alpha beta of phi is equal to the supremum of overall x and Rn of say x to the alpha, where that's a monomial of multivariate, and then we have d beta acting on phi, and so and where we have alpha and beta are inside of z plus to the n. Okay, and z plus could include 0. Okay, so these are multi-indices, if you remember. So with a metric, we have a metric space, and so we can define the topological dual space. So the topological dual space over, say, S is given as either S star or S prime. Usually I think we'll use S prime for this. S star, so S prime is Schwartz's notation. The prime notation. The star notation is much more modern. And so it's given as either this or this. I is the space of continuous linear functionals. Say T, which goes from S to C, and so the elements of S star are called tempered distributions. Okay, so that's a good start. And so turns out S star is a linear space. Linear vector is a vector space. Let's say is a vector space with a topology called the weak topology. That is given by, say, Tn converges to T if and only if Tn of phi converges to T of phi, which, remember, this is all in, say, complex numbers. And so we have a general idea of what convergence means there for all phi in short space, right? And so we'll be able to talk about approximate identities and things like that by using this idea. Okay, so these are tempered distributions. Turns out the continuity, so I was going to put this as a lemma. We're not going to prove it, but I just want to mention it. So we're going to have the continuity of a linear functional T is characterized as follows. So we say that T is continuous if and only if there exists a D in Z plus and say and constants C, alpha, and beta, where alpha and beta are multi-indices, such that we have T acting on phi, an absolute value, complex number, remember, is less than or equal to the sum of all multi-indices less than D, with magnitude less than D, less than or equal to if you want, C, alpha, beta of, say, the semi-norm P of alpha beta acting on phi. So the general idea is that if this was a norm vector space, this would be we would just say this is bounded, and this bounded property basically means that when we apply an operation, a bounded operation, in this case bounded functional, to the vector, it's going to have a limit to how much it's going to scale it up or scale it down. And so in this case, we don't have a norm space, we have a Fourier space where we have a metric, and so but we still have these semi-norms, and we're saying that basically these semi-norms don't get stretched over much. Significantly though, we only need to verify this. We only need to have this comparison with semi-norms for a finite number of semi-norms, because notice that D is finite, and so then alpha and beta, there's only a finite number of alpha and betas that satisfy this inequality. So so this is sort of a finite sum here. But anyway, so this is a fairly essential idea. Okay, so let's talk about an example. So this is called the delta function. And it is a misnomer because it's not actually a function. It is what falls under the category of generalized functions, which was, I think, initiated by Schwartz, maybe Dirac, one of those two guys. Dirac did a lot with the delta function, so often this is called the Dirac delta function. And so, but yeah. So the delta function is basically given by this. So we define say delta, which goes from, say, our Schwartz space to a space of complex numbers by this. So the delta on phi is equal to phi evaluated at 0. And this is a linear operation. I mentioned it in the video, but if, say, phi and psi are both in Schwartz space, and say C1 and C2 are scalars, then delta on C1 phi plus C2 psi is equal to C of phi at 0 plus C2 at psi at 0, which is the same as C1 of delta acting on phi plus C2 times delta acting on psi, right? So linearity check. That it is continuous is not so bad. So if phi n converges to phi n s, then we know that p of 0, 0 of phi n converges to p. So we know that Pn 0, 0 acting on the difference between phi n and phi goes to 0, which means that the sup over x and Rn, the absolute value of phi n of x minus phi n, phi of x goes to 0, which means that for any fixed x, that also goes to 0. So that means that phi n of 0 converges to phi of 0. And this is just delta on phi n, and this is delta on phi. So there you go. So continuity. So then, therefore, we've just shown that the delta function itself is continuous on the Schwartz space. So not too bad. Okay, so now we're going to define a regular distribution. So this is an example, regular distributions. Now, if you haven't had measure theory, some of the words I'm going to say are going to be a little daunting. If you want, you can just think of this function f as just being a straight continuous function that is integrable, etc. Doesn't have to be too complicated. So suppose that f is a continuous Lebesgue measurable function. My PhD advisor always had this cute shorthand for measurable. So on Rn, such that you have this. So the absolute value of f of x is less than or equal to g of x times 1 plus absolute value of x squared to the d over 2. All right. And so we're saying that this is satisfied almost everywhere. For a non-negative d bigger than or equal to 0 and a non-negative integrable function g going from, say, Rn to R. Okay, so basically we just want to use comparison theorem here. And if you don't know what almost everywhere means, it means that if I take a set of measure 0 and I remove it, then it works for all the remaining x's. A set of measure 0 would be, say, a countable set of Rn, or yeah, things like that. Say a single point would be almost everywhere. All right, so then we define this Tf acting on phi as this integral over Rn of f of x times phi of x dx. And so this is a regular distribution. So basically, a regular distribution is a distribution that we can represent using some sort of continuous Lebesgue measurable function with some sort of limit to its growth. So one example of something that is not a regular distribution is actually the delta function. So, yeah. Okay, so this defines a tempered distribution. So TF is a tempered distribution. Basically, it follows by this estimate. So TF acting on phi is equal to the absolute value of integral of Rn of f of x times phi of x dx. This we can go ahead and replace by the integral over Rn of g of x. We don't have to put absolute values on g because it is a positive function. 1 plus the absolute value of x squared to d over 2 times phi of x in absolute values times dx. So use the triangle inequality and then replace the absolute value of x by this guy here. And then what we know, this is less than or equal to the integral of Rn times g of x dx, and times the sup of x in Rn of 1 plus absolute value of x squared to d over 2 times phi of x. Okay. So we assumed that g was integrable, so that says that this is finite. How do we know this is finite? Well, we know it's finite just because phi is a tempered distribution, and I think we had this sort of equivalent definition before in the last lecture of sort of our seminorms. So this is less than infinity, and yeah, and that satisfies the definition using sort of this bounded idea. Okay, cool. Okay, and so now to talk about sort of something that's going to give us what do we call an abusive notation later. Let's show that f is actually completely determined by its tempered distribution. So we're going to say f is determined by TF when TF is a regular is a regular tempered distribution. Right, and so this is going to use an idea of a mollifier. So what we're going to do is we're going to define phi of epsilon of x is equal to 1 over 2 pi epsilon to the n over 2 times exponential of absolute value of x squared over 2 epsilon. And then we further define phi epsilon at x evaluated at y. So we fix x, and then we're going to think of this as a function of y, and then we write like this: phi epsilon at so for fixed x, we're going to write this as x minus y. Right, so this is going to allow us to talk about sort of a convolution. And so then what we can do is we can actually go ahead and take a look at our tempered distribution acting on phi of epsilon x, right? And so this is going to be written as the integral over Rn of, say, f at x times, is the integral of fy at phi of epsilon comma x, but we just said this is x minus y, right, dx. This is actually f convolved with phi, of epsilon and evaluate it at x. That is what you get there. And so, this is a convolution, in much the same way that you see a convolution, say, with a Laplace transform in, say, differential equations. And it turns out that as epsilon goes to 0, f convolved with phi of x of epsilon converges to f almost everywhere. Okay, and so that means thus f can be recovered from TF. Right, so it is completely determined by that. Something we should mention, this can be justified with an approximate identity argument. And that might be instructive to go through and do. The book in Applied Analysis, I think, has a whole section on that idea, and so you can take a look at it. One nice thing about mollifiers is that if you take a mollifier and you do a convolution with a function that's not necessarily continuous, might have jump discontinuities and stuff like that. When you mollify it, the mollification, this is the mollification, also mollification, is going to be infinitely smooth and infinitely differentiable, generally as smooth as your mollifier. And here our mollifier is phi sub epsilon. This comes up also in PDEs a bit, and so it's just good to know about. And so this gives us a collection of, say, smooth functions that would be converging to a function, smooth and also rapidly decaying, I'm pretty sure, functions that are going to be converging to f pointwise, but not in the Schwarz space norm, because in a Schwarz space norm that would mean that f would have to be back inside Schwarz space, but we didn't actually put that requirement on it. So there we go. All right, so here's an example of a non-regular temper distribution, say TD. So if I took f to be f of x equals, say, e to the c x squared, actually this doesn't even give a distribution at all, a TD. So if I take a look at, say, integral of f of x against phi of x over, say, Rn, this isn't well defined for all phi. In particular, if I were to just hit, say, if I take, say, phi of x to be equal to, say, e to the minus c, absolute value of x squared, then what we end up having is that the integral of f of x times phi of x dx is equal to the integral of 1, and that's equal to infinity, right? And so that's out. It turns out that this is a distribution because over the function, the collection of compactly supported functions, you're not going to have integral off to infinity anymore. You're always going to chop this integral off at some bound because they're compactly supported, which means they're zero outside of some radius. But since short space functions don't have to be zero outside of a certain radius, so here, for instance, it decays really fast, but not vanishing identically zero, that means that it isn't actually a regular distribution. Another one is this, and so this is again another example out of applied analysis. So the function, say 1 over x, which would say go from r without 0 to r, has a non-integrable singularity at 0, right? And so you can get a singular distribution out of this. So this is not regular. Can't so you can't bound this 1 over x with this integrable g because we know that x itself isn't integrable, so that's going to blow up one way or the other. So, but you can define, it can be used, can define a singular distribution. Okay, and the way you're going to do that is going to be called the principal value distribution. So this gives the principal value distribution, or gives a principal value distribution given by this. So it's going to be the principal, we denoted by PV 1 over x of phi, and this is going to be the limit as epsilon goes to 0 from the plus side of the integral of absolute value of x bigger than epsilon of phi of x over x dx. Okay, and so a couple manipulations that we can do here, and here, just for convenience, we're talking about S and R. It would actually, I think, be integrable if we weren't just talking about R. So here we're just thinking about R, and we started up there, so I should mention that. So this is just strictly speaking for the Schwarz space of R. So integral from negative infinity to infinity is what we're going to be thinking of. All right, so we can show that the integral is finite by this. So what we're going to do is we're going to say we're going to take a look at the principal value of 1 over x of phi, which is equal to limit as epsilon goes to 0 from the plus side, and basically we're going to split the integral into two pieces, and we're going to have phi of x, and we're going to subtract off what we get when we get phi of minus x divided by x dx. Right, and so this actually does converge. Integral from 0 to infinity of phi of x minus phi of minus x divided by x dx. How we know that converges? Well, we can split it off into two pieces. So we're going to have the integral from, say, 0 to 1, and the integral 1 to infinity. Right. So the integral from 0 to 1, what are we going to have? Well, basically, we need to show, we're going to show that phi of x minus phi of minus x over x is bounded as x goes to 0. And that's not too hard to show. Basically, we know that phi of x minus phi of minus x divided by x is equal to 1 over x times the integral from minus x to x of phi prime of x, of t, say, t dt. So this is just the fundamental theorem of calculus. And so what do we know after that? Well, this is equal to 2x divided by x times the supremum
sup of phi of x. So over all of Rn, really. It is a bounded functional. It is a bounded function, and so this is equal to 2 times sup of the absolute value of phi prime of x. So that tells us that the integral from 0 to 1 of phi of x minus phi of minus x divided by x dx is, say, convergent or well-defined. It's continuous everywhere else other than 0, so we just need to make sure that at 0 it wasn't blowing up weird. And yeah, so that's good. So we know it's bounded, and let's see. On the other hand, we have that the integral from 1 to infinity of phi of x minus phi of minus x divided by x dx is equal to the integral from 1 to infinity of x times phi of x minus phi of minus x divided by x squared dx. And in that case, we know that this is less than or equal to, say, the sup of x times phi of x plus the sup of x. So if I put everything in absolute values, that's not equal to sup of x times phi of minus x, and all of this times the integral from 1 to infinity of 1 over x squared dx, which is finite and so well defined. Okay, so there you go. That gives you another distribution that is not regular, but is well defined. So this is a principal value distribution corresponding to 1 over x, and is basically where you isolate out the singularity, and you split the integral around that. So okay, so I'm going to talk about what mathematicians call an abuse of notation. So abuses of notation are things that aren't technically true, but in the right context, it doesn't hurt anything to think this way. So for instance, in differential equations, we talk about there's an abuse of notation there when we talk about separable differential equations, and we multiply both sides by dx, and then we just have an integral with dy and an integral with dx. Now, technically speaking, dx and dy shouldn't really exist separately, and the way you would formally do it is you would use a chain rule and integrate both sides. But it doesn't hurt anything to go ahead and split those two apart, at least in that context. So and that's the same sort of thing here. And so what we're going to do is, given a t that is a tempered distribution, over, say, S, we often write for, say, phi in, say, S, we write this. So we say t of phi is equal to the integral of Rn of t of x times phi of x dx. And so this is our abuse. And so why do we do that? This comes from the characterization of regular distributions. So it comes from the characterization of regular distributions, where basically we showed that if we have a regular distribution, that you can recover the function itself from the tempered distribution. In this case, we are taking that a step further, and we're just saying, we'll just say Tx, and we'll pretend that everything is is a regular distribution, and we'll pretend that there is a function that corresponds to this. Now that is not always going to be true, but it is convenient to write. And so, and this is most often invoked with the delta function. And I'm putting that in quotes because it's not actually a function. So we'll write often delta x naught of phi, and so this is the distribution the temper distribution that gives you evaluation of phi at x naught. We write it like this: delta x minus x naught of phi of x dx is equal to phi of x naught. And so we're basically thinking of this, it's integrals over Rn, by the way. We think of this as sort of a convolution with the delta function. So so another way to express this, or what we're trying to express here, is that we're writing delta convolved with phi, and we're evaluating it x naught. Right, and so that's what that is, I think. Yeah, in some fashion. Talk about some operations on distributions. Right, and so, and generally speaking, we're going to introduce a new notation here, and this is going to be this. So we're going to say we have t phi is the same as the integral from Rn of t of x times phi of x using our abuse, and we're going to write this as a sort of what we call a dual bracket here, which is going to be t on phi. So the guys that go in here, these are in S star, and the guys that go in here are in S. And so this can be thought as input into our temper distribution here. So so we're just going to go ahead and define a whole bunch of different operations that you can do on temper distributions to give you new temper distributions. So we're going to say we're going to let f be of Rn to C be a function of polynomial growth. And what does that mean? That means that the absolute value of f of x is less than or equal to c times 1 plus the absolute value of x squared to d over 2 for some d. Say in natural numbers. All right, so it turns out that if f and d alpha of f are of polynomial growth for all multi-indices alpha, say in z plus dn, then we have that f times t is in S star whenever t is in S star. Moreover, we have that ft on phi is the same as t acting on f times phi. All right, so I'll go ahead and say, call this a theorem or a lemma or a proposition or whatever you want, and let's go ahead and prove that. It's not too bad to prove. It's going to be sort of a sketch. So basically what we're going to have is that we are looking at, say, the integral of f of x times t of x times phi of x according to our Biseau notation. And really what we want to show here is that f of x times phi of x is in the short space. So that's not too hard to show. Since f is of polynomial growth, we can say that f of x times phi of x the supremum of x over Rn is going to be bounded. And this is basically saying that P naught naught of f times phi is bounded. Right? And we know that we need to be able to put any alpha and any beta in there. So then what you know is that you're going to have phi of x and Rn of x to the alpha for any alpha multi-index, and so this is just going to be a monomial, times the derivative respect to the multi-index beta, so all of our partial derivatives taken in, sort of whatever order they need to be, times f times phi, this guy evaluate x. We need to show that this is going to be bounded. But ultimately what this gives us is we can use Leibniz rule here, and that's going to give us a finite linear combination of derivatives of phi times functions that are bounded by polynomials, and which that tells us is that this is less than infinity. More than that, we know that f times phi, and I guess we already kind of use this, is in, say, C infinity already of Rn, because we assumed that f was C infinity because we said derivatives exist of all orders and are of polynomial growth. So then that all of this above tells us that f times phi is in short space, and hence if we write f times phi, f times t against phi, which is the same as, say, f of x, which is the same as the integral of f of x t of x times phi of x dx, then this is actually the same as writing t against f times phi. Right, so that's sort of a sketchy proof there, but it gives you a general idea of what you're trying to verify. The biggest thing we're trying to verify here is that this was in the short space itself. Okay, so cool. Okay, so extending this, we're going to go ahead and take a look at this. Again, we replace t by the delta function. So we're going to have that f times delta of phi is equal to delta times f of phi, because of what we just showed. And this itself is equal to f of 0 times phi of 0. And this, on the other hand, is the same as if I just multiplied the delta function by f of 0, which is sort of interesting. So hence, the tempered distribution given by f times phi is actually the same as multiplying f times delta is the same as multiplying delta by f of 0. So the rest of the contribution of f really didn't matter. Okay. So, honestly, this might be a good place to stop. So after this, the operations on distributions are going to get a little bit more involved, and we're going to be talking about derivatives of distributions, etc. And and already we are running over an hour, I think. So so we'll just stop here and pick up later. But now we've really set stage for the next couple of things that we're going to be talking about, which are going to be operations on distributions. So we've talked about multiplication by f of a distribution where f is some sort of continuous function, a C infinity function of polynomial growth for derivatives of all orders. And now we're going to talk about shifting properties, reflection properties. We're going to talk about differentiation properties of distributions, which is interesting because we can talk about the derivatives of discontinuous functions by looking at them through the guise of them being distributions. So we'll do that. And then after that, we'll be able to talk about, we're also going to talk about convergence of distributions. And once we get all of those ideas down, we can start talking about Fourier transforms and then Fourier transforms on distributions themselves. So remember, this is all coming from applied analysis, and this is a book written by Hunter and Nocturgale. So it's a rather nice book if you want to get a lot of these ideas down. And so chapter 11, by the way. Okay, so we'll stop here, and I'll catch you. I'll see you back in my office.
Okay, that was distributions. So we went through tempered distributions, I should say. So we talked about regular distributions, give you a few examples of things that aren't regular distributions. So this sort of sets up the definitions that we need to work with as we move forward. And so we're going to talk about some transformations on distributions. If we didn't already today, I don't think we had time for it. I'm recording this before I actually record the actual lecture, so we'll see if I talk about that or not. And then after that, we can get to the Fourier transform. So that'll be 2 lectures covering short space and the dual of short space, and maybe 3, and then we'll get into the Fourier transform, so we can start tying everything together. All right, well, thanks for hanging in there with me, and I'll see you next time.